time we looked at section 1.6 on polynomials and rational functions, questions from those problems?
19.
Which?
19.
19? So 19, for each function, find the horizontal asymptote, or intercepts, the vertical intercept, the vertical asymptotes, and the horizontal asymptote. So we've got this rational function, 2x minus 3 over x plus 4. And there are four things they're asking us to find. The horizontal intercept is always found where the y-coordinate equals 0. We're interested in our graph. Where do we cross the y-axis, or the x-axis? For a rational function, for y to equal 0, the numerator has to equal 0. So in this case, 2x minus 3 has to be 0. So we can solve x has to be 3/2, or 1.5. So that's where we cross the x-axis. The vertical intercept is where x equals 0. Where do we cross the y-axis? So if we plug x equals 0 into this, 2 times 0 minus 3 over 0 plus 4, we get a minus 3/4. So that's our vertical intercept. Then it asks about asymptotes. Vertical asymptote occurs where the denominator equals 0. So in this case, whereas x plus 4 equal to 0, that's at x equals -4. And that's actually an entire vertical line. So unlike the intercepts, which is just a point on the axis, the asymptotes are either a vertical line if it's a vertical asymptote or a horizontal line. And then the horizontal asymptote, we look at the leading coefficients. So p of x is roughly equal to just 2x over x, which simplifies down to 2. So y equals 2 is our horizontal asymptote. And that's the information we're asked for. From that information, we can come up with a fairly reasonable graph of this. I mean, if we're going to be close to this asymptote and end up close to this asymptote and go through those 2 points, pretty much it's got to look something like this on this side of the asymptote. On this side, if we're going to start near this asymptote and end up near the horizontal, or I guess start more near the horizontal and end up near the vertical, here we provide an x-intercept. We don't have one, so it's got to be something more like that. So in terms of our intercepts, knowing where they are, we've already identified those key points. If we're going to start by an asymptote, end up by another asymptote, and not cross the axis, because we don't have any more intercepts, that's pretty much what the graph's going to have to look like. And we can certainly sketch it with a graphing calculator. Didn't point this out the last time. I think we graphed one, but there is a challenge with a graphing calculator. Look at here, let's see, 2x minus 3 divided by x plus 4. One challenge is definitely be sure to use parentheses so you get the entire 2x minus 3 divided by the entire x plus 4. The other challenge when we graph this, we may think, oh great, it drew the horizontal or the vertical asymptote there. What the graphing calculator is doing is plotting lots and lots and lots of points. I think 95 as it goes from left to right, and connecting them. So it plots one way up here, the next one's way down here, and so it connects them. And so it appears that it drew in the asymptote. It actually was just connecting one point to the next point. It doesn't realize right at -4, this function's not defined, because in terms of walking through this, the points it picks are, for the most part, not very nice at all. There's -4.04, -3.82. Those were the 2 points it used to plot the points. Certainly not points we would pick. So one thing we can do, there is a zoom here of a zoom decimal. And notice this time it didn't actually plot the asymptote. 1, 2, 3, 4. We don't see anything here, but if we trace this time, notice all of our x values are very nice. -0.1, -0.2, -0.3, etc. They go off the screen, so we're not even seeing these. But notice at -4, it doesn't give a value. When it tries to plot at -4, it realizes, wait a minute, I can't do that. And then it doesn't try to connect the points. Because the one before -4, -4.1, 112, it's not connecting that point to -3.9, -108, because in between it realized, oh, the function's not defined there, I shouldn't connect these points. So we do kind of have to realize what the graphing calculator is doing. It is just plotting lots and lots and lots of points. It's not trying to analyze what we're doing at all. It is just plotting all kinds of points. Another way that we could, let's see if I go back to, say, the standard. Another way we could get it to not put in that asymptote, if we come here, you may not realize, if we use this left arrow, we can go over to this icon, and there's actually multiple ways we could graph the function. The default way is just with a straight line, or connect the dots. We could connect them with bold, which you have two, you want to tell which one's which. Putting one of them bold could be helpful. We can actually shade it above, which for what we're doing really isn't what we're interested in, but there might be a time you'd like to shade above. Shade below. This is a kind of path mode. Think of watching an airplane fly through the sky, leaving some smoke. So you sort of see where the airplane is, but you're also seeing the trail it leaves, as opposed to this mode, which is just seeing the airplane fly, but it's not leaving a trail. And then there's this last mode of, let's just put dots and don't try to connect them. So if we graph this with the dot mode, it still looks pretty similar. It does not show it in the asymptote because it doesn't try to connect the dots. Some of the dots are close enough together, it looks like they're connected anyway, but some of them do have some space, and it's not going to try to connect them because we put it in a mode that just says, put the dots in there, don't attempt to connect them. So there are just different ways we could graph that, and especially with the vertical asymptote, the rational functions where there is a vertical asymptote, we expect some sort of jump. Most of our functions don't have any kind of jumps in there, but we will encounter a few that do have some jumps. Another function you're somewhat familiar with that has some jumps would be the postage function. You go to mail a letter. The postage, depending on the weight, postage starts out at 50 cents until you hit a certain weight, and then it jumps up to, I don't even remember what it is, 78 cents or something, and then it jumps up to 92 cents. So there is a certain weight. Sometimes, it was Valentine's Day yesterday, maybe you sent a card to somebody and had bought a card that says, may require extra postage. So they kind of warn you, this card may get over the limit of the extra, of just the 50 cents that it is now, and it may require some additional postage. And so there are functions that we might want to talk about that have some jumps in there, and figuring out where exactly the jumps occur could be a challenge, but these functions, the rational functions with the vertical intercept or vertical asymptote, will always have some sort of jump. Other questions?
27.
27? So 27. A scientist has a beaker containing 20 milliliters of a solution containing 20% acid. To dilute this, she adds pure water. Write an equation for the concentration in the beaker after adding n milliliters of water. Find the concentration after adding 10. How many must be added to obtain a 4% solution? And then what's the behavior as n approaches infinity, and what's the physical significance of this? So we start with 20 milliliters of 20% acid. And so we want to know what the concentration is. So we have to think a little bit about, well, how would we figure out concentration in the first place? Heck, let's go back to what they did tell us, because they told us the concentration. So the concentration here was 20%, and we had 20 milliliters. So what's it mean in terms of the concentration? In fact, can we figure out how much acid is in there? 4 milliliters. So how'd you do that?
20% of 20 milliliters.
Okay. So so 20% times 20 equals 4 milliliters. So the concentration times the amount equals, or the amount of solution equals the amount of acid. So in general, the concentration here would be the amount of acid divided by the amount of solution. So if we wanted to figure out the concentration, how much acid is in there divided by how much of the solution do we have? So we've got this situation. Are we changing the amount of acid as we do anything here? No, we're adding in pure water. So we're not changing the amount of acid. It is 4 throughout. That's what it was to start with. That's what it is throughout. What we are changing is the amount of solution. We start out at what, 20? And then we're adding n milliliters of water. So our amount of solution is the 20 plus the amount of water we've added. That's our answer for A. What's the formula for the concentration? An equation for the concentration. It's the 4 milliliters of acid we had, plus how much solution we end up with after we add in n milliliters of water, which would be the 20 we had plus what we added. Now, my suspicion is that was the hardest part of the problem. Now that we've got that, the other parts are definitely more approachable. I mean, we couldn't really do anything with B, C, D until we had this. So let's see, the concentration of 10 milliliters is added. B is just, well, what's the concentration if we add 10? So it's 4 over 30. We can pull out our calculator and figure that out. So 4 divided by 30, 0.133 or 13.33%. C asks, how many milliliters must be added to obtain a 4% solution? So in C, we want a 4% solution, and it's the n that we don't know. So just as we did with linear functions, just as we're going to do with the function we talked about today, sometimes we're just evaluating, plugging in the input, other times we're solving. Depending on the equation, sometimes the solving is much more of a challenge. So let's see, multiply both sides by the denominator. We get fact, if we don't like that decimal, we can multiply through by 100. 4 times 20 plus n equals 400. Subtract 80 from both sides, 40n equals 320. N equals, and 8 here doesn't make sense to me. So somewhere I've got a mistake.
It should be 80.
80, where?
The answer should be 80.
Okay, so, but that's still, oh, 4 times n is just 4. So the answer is 80. I was trying to figure out, 8 didn't make sense, because over here when I added 10, it only dropped the concentration to 13.3. I need to add more than 10. So the fact that I was coming up with 8 here is like, something's not right. So, just because we plug something into a formula and work doesn't mean, oh, I got an answer. Good. We should at least sort of think, does that answer make sense? And here the answer I got of n equals 8 is like, wait a minute, I think it should be bigger than that. If I had 20, 8's not going to do it. And 10 certainly didn't get me close to 4%. So it's like, what did I do wrong? And my error was here as I was distributing through, I stuck in an extra 0. So we do get 80. And then the last question they asked, D, what happens with this is n goes to infinity. So our concentration again is 4 over 20 plus n. This is a rational function. Here, however, the degree of the numerator and the degree of the denominator aren't the same. The degree of the denominator is larger than the degree of the numerator. When that happens, we have a horizontal asymptote of 0. Or we could just sort of think, if n's really big, 4 divided by a really big number plus 20, then that's going to be a small number. Think of 4 cookies, or four pizzas. We'll do pizzas. 4 pizzas. If you try to divide 4 pizzas with everybody on campus, nobody's going to get much pizza. And if you invite more people than everybody on campus, everybody's going to get even less. The more people you invite, if there are only 4 pizzas, the more people you invite, the less there's going to be for everybody. Ultimately, it goes down to 0, which means then the physical significance of that is if you keep adding water, keep adding water, keep adding water, the concentration is going to go down to 0. And if we think about that a little bit, hopefully that makes some sense. I mean, if we start with acid and keep diluting it, keep diluting it, keep diluting it, eventually the acid's going to be unnoticeable in our solution. Okay, other questions? Okay. Well, if you could pass that homework forward, or if you still need to work on it a little bit, bring it by my office later today. Didn't know if that was homework.
Sorry, give 2 seconds.
Okay, we would get 2 more days of new material, counting today. And then we'll review next Thursday. Our first exam is actually coming up a week from Tuesday, so the 27th of February. I do have a review sheet. I'll go ahead and give it to you now. One of the problems with a Tuesday, Thursday class is kind of figure out, well, how do we use our time efficiently, especially in preparing for an exam. And so we will review some on Thursday, but I've also scheduled in a review session Monday night for additional review. Probably tapped a few too many and down a couple rows. Did I get enough? I was thinking we've got like 3 people out. I should have a few more somewhere. So on the review sheet, let's see if I can pull that up here. Apparently not. I have the sections listed, and some topics from each, some additional problems you can look at in the book to review those materials, and then the 21st, which I think is next Wednesday, answers will actually show up that you could look at to see those answers. And then there are also some additional worksheets. You can practice some things, and we'll have the review session the night before. But as I said, we've got 2 additional topics to cover. So we've been working kind of, our first model was that of linear. We start with a certain amount and we add a certain amount every day or every time period, and that gives us the linear equation y equals b plus mx. And for a lot of situations, that makes sense. Somebody's going to pay you $100 a day plus 3% commission on your sales or something. I mean, there's a certain amount plus something that depends on how many things you sell, different types of scenarios that way. So that's a linear. But there's another way we can model growth that is helpful, especially in business settings. It can be very helpful. And the idea is, say, we start with 10 people, and every month, everybody gets somebody else to join. So we can still look at a table here. So we start with 10 people. After 1 month, how many people are we going to have? If everybody goes and gets somebody else to come join that church, what are we going to have in 1 month? Sorry, with the clicker.
Sorry, I was totally.
Let's see, you said 20, so did everybody else. Most everybody's already saying 20 before you said 20.
Totally not that.
So we're up to 20. What if we do this again? So we've got the 20, everybody goes and gets somebody else to join. What are we going to end up with? And here's where the difference comes in on kind of how we think about this. Because a couple of people said 30. We added 10 the first month, we'll add another 10. Well, if we keep adding the same amount, that's linear. But we're now up to 20 people, they go and find another 20, so we actually jump up to 40. The next month, we would jump up to 80. So there is an additive feature going on here. We added 10, we added 20, we added 40. What we're adding is not the same amount, so it's not linear. However, what we are adding is the same percent of what we had. Each time we're adding 100% of what it was. We're adding 100% of what it was. We're adding 100% of what it was. Or more easily to spot, in this particular case, each time we're doubling. We double, we double, we double. So there is an additive pattern that we could look at. There's also a multiply pattern we could look at. And kind of depending on the situation, sometimes we'll focus more on the additive pattern. What percent are we adding? Other times we'll focus more on the multiplicative pattern. But the additive pattern is not that we're adding the same amount. It's the same percent. And when you get a little bit more in there, the percent that you add, I mean, the actual amount you add is higher because you had more to start with. So adding 100% the next time is more than adding 100% the first time. So we could go and we could fill out this table, and this grows extremely rapidly, doubling every month. Don't think there are too many churches that could handle this very long. Certainly at some point we'd run out of people in the town, and so it'd be a problem to continue to double every month or even double every year. And yet there are lots of things that are modeled with exponential. And that's what we're looking at here, is what's called the exponential equation. In this case, the number of people is 10 times 2 to the nth power. 10 is our initial amount. And 2 would be called our growth factor. What are we multiplying by each time? And as we see here, it grows much, much faster than linear. And we'll look at graphs specifically in a little bit as well. But it's a multiply, where we multiply over and over and over again. So by the time we get down here, we've multiplied by 2 3 times. And that's why we see the exponential on here. 2 to the third power is 2 times itself 3 times. Well, that's what we've done by this point. 2 times itself 3 times, times whatever we started with. So if we kind of compare these two, here we had the initial amount in linear, that was B, and M was our rate of change, or our slope. In exponential, there's still an initial amount that we can identify in the equation. There's still something about the growth. It's just what are we multiplying by, not what are we adding every time. And sometimes we'll multiply by things that are less than 1. We get less, so we lose a certain percent. Next time we lose a certain percent. We lose a certain percent every time. So if it's the same percent, even if we're losing it, we end up multiplying by some number. If we're losing a percent, the number we multiply by happens to be negative. So the form of the equation, there are a couple forms we could look at. One is y equals a times 1 plus r to the x, where we focus on what rate are we changing? Are we adding 100%? Well, 100% written as a decimal is 1. Are we adding 10%? Are we losing a certain percent? Other times we'll focus on what are we multiplying by? Here we're multiplying by 2. But in either way, A is the initial value. It's what we start with. And then R or B is telling us something about how is our amount changing. And there are the two different ways we could really think of the amount changing. We're adding a certain percent, or we're just multiplying by a certain value. And R would be called the percent growth or the percent decay rate. Normally we write it as a decimal, and it will be negative if we have decay. And B would be called the growth factor. And there is a relation between these two. The growth factor equals 1 plus the growth rate. And if it really is growth, the factor is bigger than 1. If the factor happens to be less than 1, we have decay. So let's begin to think about where might we see this. If we're given some information, where might we see this? Well, one, we could just be told the initial amount and what percent. So say we've got 20% bacteria, and they're growing at a rate of 20% each hour. Oh, so 200 bacteria, sorry. 200 bacteria, they're growing at a rate of 20% each hour. Well, we'd like to know, well, how many are we going to have in 5 hours? Or that's one of the questions. So our basic model is this one, the initial amount times 1 plus the rate to the x power. So based on what they've told us so far, what are we going to be trying to compute here? Which of these 4 options are we going to be trying to compute? Yes. No. Not at all, or?
Baseline, I will answer.
I don't know if we need to get back on the BB frequency, or? Yeah, I think it may have turned off. And yeah, if your clickers ever do turn off, they've got to get reset to the BB frequency when you turn them back on. And probably they did turn off between signing in and now. So let's see. Most of you said the 200, which is the initial amount, times 1 plus our rate, and the rate does go in as a decimal. We write it as a percent, but in as a decimal to the 5th power. Then we can pull out our calculator. So 200 times 1 plus 0.2 to the 5th power. Now when you pull out the calculator, you've got to be careful how you put it in there. But it goes up to 497, with bacteria we'd probably say round it up to 498. So the 20% is kind of an approximation. And you might even say, well, how did they know it was growing at 20% each hour? We'll talk a little bit about that as well. But suppose we know kind of how it's growing, we can make predictions into the future. So we just plug into our formula the information they gave us, and in this case it's an evaluate. We had the initial amount, we had the percent, we had how long we were going to do it. It was just an evaluate problem. Now, if we wanted to know, well, when would we reach 1,500 bacteria? Well, for that we would need to solve. Because we have the amount we want, the initial amount times 1 plus the rate, to the x power, we need to solve for that exponent. Well, that's a much tougher problem. It's a very interesting problem. It's one we certainly want to address, but we're going to delay that till the next time. We're going to focus on exponential. So it may feel a little bit like we're only doing half of what we might want to do, to evaluate half, and we are. But we need to get comfortable with the evaluate half before we come back to focus on, well, how do we solve? Now, we may be told the initial amount and then how much we have at a later time. So we may be told something, a city's got a population of 20,000, and in 6 years later it's up to 21,000. So we start with 20,000, 6 years later we're up to 21,000. We're going to assume exponential growth. Pretty much when you're talking cities, bacteria, investments, there's an assumption that it's growing exponentially. And so we assume our model is y equals a times 1 plus r to the x power. If we see that phrase, assume exponential growth, this model, or if you prefer, the model with the b in there. So if we plug in the information we do know the initial amount. They told us that. They didn't tell us the rate, but they did tell us how long we're doing this and what our final result was. Now again, we've got to solve. This solve, though, is actually easier than this solve. This solve we've got some experience doing. We can divide both sides by 20,000. Let's see, 21 divided by 20. 1.05 equals 1 plus r to the 6th power. How do we handle solving when there's this 6th power involved? How would we handle it if it was squared? Yeah, if it was squared, we take the square root. When it's higher powers, we can still take a root. In this case, it would be the 6th root. So we would need to take the 6th root to solve. Depending on your calculator, maybe you can find the 6th root. This calculator does have it under math, this x root option, but we kind of have to think about how we do it. We have to say the 6th root of, and then what number do we want that of? So it's a little awkward in how we put it in here maybe, but what root do we want, and then what do we want it of? We get here 1.008. 2. Certainly we're going to be talking some fairly long decimals. The question will be, well, how many places do I need to write out? The reason I went to the 2 rather than just 1.008, notice here the 1 is going to go away as I solve for r, and I really wanted more than one significant digit there, in the 0.008. So I thought, well, let's just round it to another place. And so our rate here then is 0.0082 or 0.82%. When we see it written out in the equation, it's a decimal. Typically when we talk about the rate, it's written as a percent, so 0.82%. So not really growing very rapidly, but it's growing at 0.82% every year. Kind of like interest rates. I remember a time when interest rates of 4 or 5, even you maybe find 8% interest. Can't do that anymore. You're lucky maybe if you find a long-term CD at 1.2% interest. That's just not right. And you may even have some, probably grandparents that a few years ago when that switch came about, had to rethink retirement plans, because retirement plans are sort of based on your income is going to continue to draw 8%. Well, if you drop from 8% down to even 0.82%, you're not getting as much money coming in, and it becomes a problem at that point. So this idea of exponential growth is extremely important in lots of investment scenarios, and certainly in a growth scenario like this, is the town is thinking if we grew that much in 6 years, then we'd ask a question, well, say what's it going to be in 2030? If this rate of growth continues, once we have our model, so we've now decided 1 plus r is 1.0082, we can then use the model to make predictions into the future. So the amount is 20,000 times 1.0082 to the x power. So in terms of 2030, that's 20 years later. And so we evaluate the model we came up with when the input is 20. And we get then, let's see, 20,000 times 1.0082 to the 20th power. We're up to 23,549 if we round it. Now, in terms of at what point do we round? If you show me what you put in your calculator, I'm not going to be all that particular about did you round in exactly the right spot or not. I can usually tell, even if you rounded this to 550, that you just rounded the answer. But we don't want to round too early. I mean, a temptation on this might have been, oh, 1.0082, that just rounds to 1. Well, if you round it to 1, you throw away too much, the population stays 20,000. So we definitely do never want to round this just to 1, even if it looks like it's really, really, really close to 1. The fact that it's a little bit bigger than 1 is what's giving us the exponential growth. So we don't round it there. And we may even go back to what we did here. So another way to get the 6th root would be to take 1.05 to the 1/6 power. And if we use that whole expression, 20,000 times that to the 20th power, 23,532. So even what we did here in rounding, if we'd used 20,000 over I shouldn't even say exact here, the more digit approximation to the 20th, we come up with 23,532. So in this case, that subtle little difference we got in rounding didn't make a huge difference. But we're going to look a little bit that with exponential growth, often even just a subtle little shift in the percent return, long term, could make a huge difference. And I don't know, some of you may be looking at going into like investments or financial advising of people. There's a huge difference between if you can get the retirement savings to earn 5% as opposed to 6% over 40 years. There's a huge difference in that. Now, we can again ask, well, at what point would this population reach 25,000? So when does our model get us to 25,000? Well, again, that's a question that we're interested in, we'd really like to be able to solve, but at this point, we can't yet. That's what we'll look at Tuesday. It is how do we solve an exponential equation when the unknown is up in the exponent. When the unknown's in the base, we can do it by taking a root. We need another function for solving it in the exponent. But let's look at a couple other examples of things here. So, if we start with an equation, we should be able to, from the equation, identify immediately, what are we multiplying by every time? So in y equals 2,000, or 200 times 3 to the x, what are we multiplying by every time? And what we're multiplying by every time is the 3. Whatever is being raised to the x power. The 200 is what we started with. Which probably was my next question I just answered for you. But we're multiplying by 3 every time. Actually, my next question is not. My next question is, well, what's the growth rate? If we're multiplying by 3 every time, and the growth factor equals 1 plus the growth rate, what is our growth rate in this case? By what percent are we growing as we multiply by 3? So using our formula here, the growth factor is 3, so the growth rate equals 2, but we always write the growth rate as a percent. 2 written as a percent is 200%. And notice here, if we focus kind of on what we're adding, here I added 400, which is 200% of what I had before. It's a 200% increase added on to the 200 we already had. Here we're adding 1,200. Well, that's 200% of where we were before. So the growth rate in this case is 200%. So the rate we always write as a percent, even though our initial calculation may get it just as a number, we have to convert that over to a percent. And the initial amount I already told you was 200. Now, as I said, one place this definitely comes up all the time is the idea of investments. You invest some money, it gets some interest. At some point, that interest goes into the account, and the interest starts getting interest. So you get what's called compound interest. With compound interest, there are a number of ways you could do this. One is just wait till the end of the year. At the end of the year, put in the interest. So if we're compounding it annually, which is not the way it's typically done, but our amount is what we put in the first place times 1 plus the rate to the t power. How many years we've had this done? Because in the case of compounding annually, we go a year, we get r% interest. We add that to what we had. Well, adding r% is the same as multiplying by 1.r, or 1 plus r. And we just do that every year. So, we could look at some investment scenarios. If we invest $1,000 at 8% compounded annually for 2 years, what formula would we use at that point? and it would be C here. The initial amount is 1,000. 1 plus the rate, 1 plus 8% is 1.08. That's what we multiply by. And again, there are kind of the two ways we could think of this. We're adding in 8% of what we had, or we're multiplying what we had by 1.08. In fact, let me do one other thing. I hadn't thought about that. So, in business, a lot of times you probably use Excel. So we've got so let's see. We'll go for the number of years. So at year 0, our balance is $1,000. And we don't get any interest. Then each year, well, it's going to be 1 year more than it was before. So the years are going to go up by 1. The next year, the balance is going to be the interest we get from the year before. So I guess at the end of the year, we are going to get, in this case, 8% of what the balance was. Equals. So the first year, we do get $80 of interest. The next year, though, our balance goes up because our balance is what it was, and we add in that interest. That's the idea of compound interest. So we get a little bit more interest because our balance is bigger. So at the end of that year, we get 8% of the 1,080. And that continues. And so notice in about 9 years, it doubles. Close to doubling in 9 years. So this was focusing more on just let's add 8% in every year. We get the same thing if we looked at our balance here of 1,000, and we always just take the previous amount times 1.08. It's going to give us exactly the same numbers. The formula multiplying by 1.08 is much easier than feeling like, oh, I've got to fill in this whole table to figure out what do I have, 10 years down the road or 40 years down the road. So if we take this thinking, investing for retirement, so 40 years down the road would be down here, up to 21,000. Same number we would get here if we take it 40 years down the road. We have exactly the same amount. And notice we're getting more interest every year because our balance is bigger. But instead of taking that interest out, it goes back in. And that's the idea of compound interest. You get interest, it stays in the account, it draws interest, it gets interest, and really any long-term investment, that's what happens. And that's why when you get out and get a job, and some of you may be advising people, the earlier you start retirement savings, the better. Because what really kicks into retirement savings is not the money you put in, it's the compounding effect that you receive over the course of time. In fact, now that I've got this, let's modify the scenario just a little bit. And let's do it with the multiplying, because that'll be a little easier. So suppose we only get 7%. So I multiply that times 1.07. First year it's $10 less. Well, what's it going to be over the course of 40 years? What kind of difference is that going to make? Over 40 years, it's $7,000 less. So that first year didn't seem bad. It was only $10 less. But with the compounding over and over and over again, there's a huge difference even between 7% and 8% if you're in a position to leave it there for 40 years. And for retirement, that's kind of the idea. You start saving some money, it's going to be there for a long time. If, on the other hand, maybe we could get 9%, so this times 9%, or times 1.09, we get $10 more there the first year, but over the span of 40 years, we get $10,000 more than we had over the 8%. So that extra 1% makes a huge difference if we're in a position to let this go long term. And that's a key idea behind any sort of investment. The compounding is what's really bringing in the money. So, and the advantage the formula has is, we could ask specific questions. What do you get in 40 years? I mean, with Excel, it's easy enough to do that, but we wouldn't have to fill in all the tables. Certainly in days before Excel, you would want this formula. You would not want to have to figure out every year of the 40 years just to figure out what's happening in year 40. You'd like the formula. So we can figure that out. We'd also then be interested, well, when would it reach 10,000? Now, with Excel, I suppose we could go and put that in here, and we could figure out kind of roughly when it reaches 10,000. Sometime in this year, or by the end of this year. But in general, we'd like to solve that more exactly. And so again, we're faced with this dilemma of, oh, here's an exponential equation. I don't know the exponent. That's what we'll look at on Tuesdays. How do we solve those kind of problems? Now, let's think of another application that I think happens in business a lot. Things are losing value. I mean, you make an investment, you hope it gains value, but you buy a car, you use a car, the car depreciates over time. So suppose you get a company car valued at $20,000, and they decide, well, it's depreciating at 30% each year. So each year it loses 30% of its value. And we'd like to know, well, what's its value in 6 years? Suppose we could also do that with Excel. In fact, let me just change a few things here. So what changes is, in this case, our balance, we're starting at $20,000. And we're losing 30% of the value. And so the new value is what it was minus what we lost. So the first year it dropped $6,000 in value. Well, now it's not worth as much, so the 30% it loses is not going to be as big. It's going to lose the next year only $4,200 in value. And so again, we could look to follow that through. What's the value going to be over time? Or if we use this model, since we're losing value, our rate is actually negative. So we're multiplying by 0.7 to the t power. So over here, where it was 1,000 before, it's 20, and now instead of multiplying by 1.08, we're multiplying by 0.7. And notice we're getting exactly the same values. Let me just get rid of those. And notice in this, I mean, if we extend this on down, indefinitely, it never really loses all its value. I mean, sort of it does, but really doesn't lose all of its value. So what's different here when we are losing value is 1 minus the rate. And so we're losing 30%. We're left with 70% of the value. But still, from the description, we can identify the initial amount. We can identify, well, how many years are we talking about? And we can identify what's happening with the growth, or in this case, decay. And so we can plug that in, solve it with our calculator. Then we also might want to know, well, when's it going to be $1,000? And we'd have to solve that equation. I mean, here, $1,000 we hit somewhere around year 10 and 11. We still don't know exactly where that is. Here's another exponential we would need to solve. So as we work with exponentials, we're really only positioned now to evaluate. And we just have to decide, as we see different questions, what's the initial amount? What are they telling me about the rate? Now, back to the idea of compounding. Most banks don't just compound once a year. They compound more often. So if they compound n times a year, the formula modifies slightly. The amount is the principal times 1 plus the rate over n to the nt power. The n times a year, that n shows up in two places. The rate divided by n, because we're getting, say, 8%, but we're doing it 4 times a year. Each time we compound, we're really only getting 2% added to it. But we're doing it 4 times more often. And notice, annually is n equals 1. And if n is 1, it's exactly the same formula. And so we can say, well, if we invested $1,000, say at 6% compounded annually for 2 years. Actually, let's skip that one. I want to make sure. Let's look at this one. So 6% compounded monthly for 2 years. What formula would we need to be putting into our calculator? So it's $1,000. The rate, I said here, was 6%. Monthly, well, there are 12 months every year. And the 12 shows up in 2 places, and then we were doing this for, what did I say, 2 years? And so we get B here. We can plug this into our calculator and come up with our result. We do have to watch how we put it into the calculator. 1,000 times 1 plus 0.06 divided by 12. If you don't put parentheses around the exponent, it will do to the 12th power first, figure that all out, and multiply that result by 2. So you need to be sure either to do the 12 times 2 in your head and put 24 in the exponent, or make sure you've got parentheses so it does an exponent of 24. If you're not careful in putting it in the calculator without the parentheses in that exponent, the calculator will do a computation, it's just not the one we want it done. We want it doing. So, and it goes up to $1,127, which, let's see, is a little bit more money than if we just did it annually. We get like $4 more compounding it monthly. But we do get a little bit more. Well, somebody decided, why stop at, say, monthly, 12 times a year, or daily, 365 times a year, every day. We can do it every hour of every day, or every minute of every day, or every minute of the year, and get n bigger and bigger and bigger. So as we think of n getting bigger and bigger and bigger, we get what's called compounded continuously, which in a sense with bacteria growth and things like that, that's kind of how they grow. They're always growing, and so compounded continuously, we get a different formula. The amount equals the principal times e to the RT power. E is on your calculator. So when we need e to a power, we can let the calculator do that. E to the first power would be e if you want to know what it is. It's an irrational number, much like pi. Just keeps going and going and going, even though it kind of looks like it repeats, it does not. But when we need to do a computation, we'll let the calculator do e to a power. So we do have some different forms of the formula. With that, and I'm pretty much out of time. I'll double check things here and make sure I haven't missed anything important. And your assignment is available on Blackboard.